Hello, this is part 2 of our beam lift demonstration. This is a picture of our downhole beam pump, and it is reciprocating up and down. You can see the action of the plunger. This is the plunger. There's the traveling valve that closes on the upstroke and opens on the downstroke. And this is the standing valve that opens during the upstroke and closes during the downstroke. Right now, the plunger is lifting, the barrel is filling on every stroke with this sort of yellow-colored mineral oil. So this is the vertical part of our well. We have a slide that showed the anticipated flow regimes of gas and liquid in a vertical section. So the slide that is the vertical flow regime map is talking about what flow patterns you might see here in the vertical annulus. Right now, there's nothing but air in there. There is no oil. The oil is being picked up into the pump through the end of this long dip tube, which we'll see in a minute goes down to the end of our horizontal section. But if there were some liquid in here, the air moving through it would make it change into a different pattern. Now, traditionally, beam pump specialists believe that an air velocity going up the annular space of 10 feet per second is about as much air as you can risk in the vertical part of the well, mainly because most of the time the pump intake is here in the vertical part of the well. So even if I have a downhole gas liquid separator, it will struggle to keep the gas and the liquid separated if the gas is moving up the annulus faster than about 10 feet per second. So we're going to demonstrate what that might look like here in a little bit. Now the other part of our well is this horizontal section that comes all the way out, all the way down to the end, where we have the end of our dip tube. This is the end of our dip tube. And you can see right now the horizontal part of the well is substantially full of our yellow mineral oil. It is submerged, so the only way into the pump is to enter the dip tube, and it's submerged in the oil, so only oil is going in there. The air would sheet across the top of the oil-air interface and head on to the vertical part of the well where it would go vertically up and be vented at surface. Now there's another graphic in the second slide that shows the flow regimes in the horizontal part of the well. There is no particular standard for the maximum air velocity, other than we would really like to keep the air from being able to enter the end of the dip tube down here. We would like to keep that submerged. So I'm going to turn the air rate on now, and let's see what develops. I've got a Coriolis meter over here that shows the air rate as a mass flow rate. That's kilograms per minute. And if I wanted to get to that theoretical air maximum velocity in the vertical part of the well, that would be about 1.9 kilograms per minute of air. Right now, it's reading 0. I haven't turned the air on, but I am about to change that. All right, you'll notice that we have about a half a kilogram per minute of air. So we're nowhere near that theoretical maximum velocity. And let's take a look at what it looks like. So here in the horizontal part, the air is coming in all the way down here at the end. And if you look on up the long lateral, the long horizontal piece, you'll notice not much has changed. The air is moving along the high side of the horizontal piece of pipe. It's going up into the vertical part of the well, and it's not carrying any liquid with it really at this point. So nothing particularly has changed. If you look at the horizontal flow regime slide, we would probably call this stratified flow. Stratified because the air's on top and all the liquid's on the bottom. So I'm going to add a little more air. Okay, I'm up to a little more than 1 kilogram per minute now. And there's a little bit of a change in the profile in the horizontal part of the well. There's a little bit of a ripple across the top of the liquid. I think, however, we would still call this stratified flow, and the end of the dip tube is still submerged in the liquid. So there isn't anything different going on yet in the vertical part of the well. The vertical part of the well is still just picking up the liquid that comes in from the end of the dip tube down here and lifting it to the surface. So nothing really has changed from the vertical part of the well yet. We are still submerged at the dip tube. And the only real change in the flow regime is maybe a little bit of rippling effect going across the stratified top of the oil and the air. All right, I'm going to add a little more air. Now, the dip tube is still basically submerged. There's a lot more air velocity going across the top, and if you'll look at the pattern going towards the well now, things have changed dramatically. It's still stratified, but it's kind of frothy on top, and now look at the vertical part of the well. What about that? So we now have a lot of air that's lifting the oil way up into the vertical part of our wellbore, and we are right at the 10 feet per second mark. So you can imagine the problem that if we had the pump intake here in the vertical part of the well, the problem of keeping the gas out of the pump intake, it's probably not feasible. That's why that 10 foot per second limit was employed. Now, I'm going to turn the air off just to show you quickly what's going on in the pump. So we'll let the foam and the froth subside here. And I want you to look in the barrel of the pump. it is essentially still full. That's because the pump intake way down here at the end of the dip tube is still submerged. And you'll notice the barrel, it's hard to see with all of this froth in here, the barrel is still full of liquid. So even though it looked bad when we had all of the foam and froth at 10 feet per second of air velocity, it had no substantial impact on the action of the pump because the dip tube, way out here in the end of our horizontal, was still submerged in liquid. So it was sort of disconnected, if you will, by the dip tube being out at the end of the lateral, as opposed to the pump intake being here in the vertical part of the well. So it looks to me like from this quick experiment that maybe the 10 feet per second gas velocity rule isn't too bad. Less than that, we don't have enough gas velocity to really foam up to carry the liquid up into the vertical part of the well. Above that, we certainly do. So the lesson here is the gas velocity is important. It describes the flow regime that we expect to see in the well, regardless of whether it's the horizontal part or the vertical part. And it also ties in to where is the intake to the pump. If the intake to the pump is some sort of gas-liquid separator in the vertical part of the well, that frothy, chaotic flow due to the gas being at 10 feet per second or faster probably exceeds the capacity of that separator to really do its job, and we have a bunch of air or gas entering the pump. The way we have it set up here with the dip tube down in the curve of our lateral, the dip tube is more than likely staying submerged and allowing the casing to act as a wonderful gas-liquid separator by itself.